Assalamualaikum warahmatullahi wabarakatuh. Good morning, friends and everyone. We are from Group 6 of the Ordinary Differential Equation in the International Class of Mathematics Education 2019. Here we are going to present about the pendulum without damping, that is the application of second order differential equation. Okay, next. The members of our group are me, Afrian Frizky Alanda, and Khoirul Mubin Fatyadi, and Lutfi Anggito Wicaksono Aji. Okay, let's we discuss about the simple pendulum. A simple pendulum consists of a mass M swinging back and forth on the end of a string, or better a massless rod of the length L. You can see in the figure in the beside. We might specify the position of the mass at the time t by giving the counterclockwise angle theta is equal to theta t that the string or rod makes with the vertical at time t. To analyze the motion of the mass m, we will apply the law of the conservation of mechanical energy, according to which the sum of the kinetic energy and the potential energy of the m remains constant. So we use the conservation of mechanical energy. Okay, next. The distance along the circular arc from O to M is equal to S is equal to the length of capital L times theta. So the velocity of the mass is V is equal to the ds over dt is equal to L times d theta over dt. And therefore, its kinetic energy is equal to T is equal to a half of M times V square, where V is in the previous, and we get a half M times ds over dt square, and we get a half M times L square times d theta over dt square. And then we next choose as reference point to the lowest point O reached by the mass. That is, V is equal to M times G times L times 1 minus cosine theta. And then its potential energy V is the product of its weights mg and its vertical height. H is equal to L times 1 minus cosine theta above O. So we get a half M times L square times d theta over dt square plus mgl times 1 minus cosine theta is equal to C. And then we differentiate both sides of this identity with respect to t. And then we obtain ml square times d theta over dt times d square of theta over dt square times plus mgl sinus theta times d theta over dt is equal to 0. And then we get d square of theta over dt square plus g over L sin theta is equal to 0. And then after removal, the common factor ml square d theta over dt. Okay, the next. The next will be explained by my friend Khoirul Mubin Fatyadi. Please, time is yours.
All right, thank you. The next is pendulum without damping. It's actually the simple pendulum. Okay, let's see the picture. The picture. We shall use Newton's second law to construct a mathematical model of the motion of the bob. Let G be the acceleration of the gravity. Since we ignore air resistance and friction at O, you can see up at the point O, no damping. There are only two forces acting on the bulb during the motion. One is the weight of the bulb with magnitude mg Newton and direct downwards, and the other is the tension of the rod with magnitudes the newtons and directions along the rod. You can see the picture to find the result of force on the bulb in the tangential tan- tangential directions. We must resolve the weight into two components. By Newton's second law in the tangential direction, we have the equation 2, that is m d double prime s over dt square is equal to negative mg sinus theta, and differentiating equation 2 twice with respect to t. Remember that L is constant. We obtain for 0 for t between 0 and infinity. The second order differential equations is theta double prime t is equal to negative omega square sinus theta t. We get equation 3, where a prime L denotes the derivative with respect to t, and the parameter omega is given by omega is equal to the square of g over L. We get equation 4. Okay, next is now we recall that if Uh, we, we recall that if, oh, I'm sorry, it's short, there's theta. Theta is small, and the sinus theta approach to theta. This approximation obtained by retaining just the first term in the Taylor series for sin theta. In fact, sinus theta and theta agree to two decimal place when the magnitude value of theta is at most 3 over 12, that is 15 degree. In a typical pendulum clock, for example, theta would never exceed 15 degree. It therefore seems reasonable to simplify our mathematical model of the simple pendulum by replacing sinus theta with theta in equation 1. If we also insert a term c theta 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 prime to account for the frictional resistance of the surrounding medium, the resulting in equation in the form of equations uh, theta 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 double prime plus c theta prime plus k theta is equal to 0, where k is equal to g over L. Note that this equation is independent of the mass m and on the edge of the truth. Okay, next. Oh, the next, it's interesting to note that had the pendulum been a rigid body of the shape and mass distribution which cannot be modeled as a simple pendulum, we would have used a more complicated mechanical of rotation body, which will fall outside of the scope of this book. But in the end, we'll have obtained the same equations with only the different parameter omega. If you happen to know the mechanical term, we live we have in this case that omega square is equal to GHK power negative 2, where h is the distance from O to the center of gravity, and k is the radius of the duration of the body. Let the initial position and the angular velocity of the pendulum be respectively theta 0 is equal to alpha, and theta prime 0 is equal to beta. Okay, you can see the graph, the sketch of the graph of the pendulum without damping. That's all. Okay, for the next is what is it? Example. Example will be explained by Lutfi Anggito. Okay, please, Lutfi Anggito.
Okay, thank you, Mubin. I will explain the next, that is example of pendulum without damping. So here's a problem. So there's a pendulum with length L on meters to oscillation. If the frequency of the pendulum is equal to 5 over 4p with g equals 10 meter over second square. How is the solution of differential equation in the pendulum? So here's the alternative solution. So given the frequency equals 5 over 4p hertz and the gravity equals 10 meter over second square. So the question is why t? And then the answer, the form of differential equation can be given as follows: d double prime theta over dt square plus g over L sinus theta equals 0. Note that g over L equals omega square. First, we find the value of L. That is, L equals t square times g over 2 pi square. That is equal t equals 1 over f equals 1 over 5 over 4p. So that we get the t equals 4p over 5. Then we substituting t equals 4p over 5 into L. Then we get L equals 4p square over 5 times 10 over 2p square. And then L equals 60p square over 25 times 10 over 4p square. And then we get L is equal 1.6. So we get the length of pendulum is 1.6 meter. After that, we found the value of omega square. That is, omega square is equal g over L. So that omega square is equal 10 over 1.6, and then the omega square is equal 6.25. Then we determine the solution of differential equation on pendulum, and then we get d double prime theta over dt square plus g over L sinus theta equals 0. And then theta double prime plus omega square theta equals 0. And theta double prime plus 6.25 theta equals 0. So the characteristic equation is lambda square plus 6.25 equals 0. And then the root are lambda 1, lambda 2 equals 0 plus minus the square root of 0 square minus 4 times 1 times 5.25 over 2 times 1. That is equals plus minus 2.5i. So we can see that in this case, the alpha is equal 0 and beta is equal 2.5. So the solution is given by y equal C1 cosine 2.5t plus C2 sinus 2.5t. So that is the presentation of our group. If you have any question, feel free to us to our group. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.